a polar function is something that's defined piecewise by a third parameter, a t. So this function outputs things of the form t comma xy. Those are the ordered pairs that are in our function. This allows us to graph something that fails a vertical line test, but still is a function in terms of t, right? Because x and y are what we're plotting, but the input to our function is this invisible parameter t, right? So if I have t equals 1 and t equals 2 that both give me the point 1, 2, that would fail a vertical line test on my graph, but it would still technically be a function because the t, the input, was different even though we had the same point. Is that okay with you guys? Okay. A polar function is something that's in the form like, well, r equals like f of theta. I'll just write it that way, I guess. So here, again, what we're getting is points that are r comma thetas. So my function are these ordered pairs r comma theta. And we can convert these into xy's. And the reason that this is will allow us to get things that are not functions is because if I remember like 3 comma 30 degrees is the same as the point like 3 comma 390 degrees. Those are the same xy, right? These are technically different ordered pairs in terms of r and theta, but they are the same xy point. So again, we can get things that are still functions as a polar function, but produce graphs that fail a vertical line test. Remember when we graphed polar functions, we got all those like rose curves and stuff coming out of it? Alex?
So the theta comes in as the angle of the
Theta is an angle measure. Yeah, so basically these polar coordinates are like vectors. You have a length, and r is a length, that's the distance from the origin to the point, and theta is the direction. It's basically just drawing, like using a vector to describe the location of the point. So like the terminal point of the vector is the r theta. It's like a magnitude and a direction.
It's like a theoretical thought of it being an xy.
Well, right, because we can convert that into an xy coordinate by the same way we would with a vector by converting it into component form.
Yeah.
So it's the same notion there. Right, so like if we have like 3 comma 30 degrees, what you have is something that's 3 long at an angle of 30 degrees. And we could convert that into like an x and a y by doing like 3 sine 30 and 3 cosine 30, right? And we could certainly have another point that's like, here, whatever this is, that would fail a vertical line test because these 2 points are on the same vertical line, or the same xy points, but the r and theta are going to be unique compared to the other r and theta. So like in terms of a polar coordinate or polar function, this is still a function, right? They have unique input and output. They just fail that vertical line test when we talk about things in a rectangular coordinate system. Is that okay so far? Okay. So we had these two different types of functions, and we kind of explain now like why we should care, because it gives us additional flexibility to describe things as functions that we could not using our like rectangular coordinate system, right? So like a circle we can describe as a function with a parametric or a polar, and we couldn't do that in a rectangular sense. So what we then did is we worried about converting between rectangular coordinates and parametrics and vice versa. So let's say we have some rectangular function that's of the form y equals f of x. To convert this into a parametric, it's really, really easy. We'll just take the function x and write that as t, and then our function for y will just be f of t. So it's like trivial almost to convert these from rectangular to parametric. The only thing that we have to be careful about is the domain here is going to have to transfer to our domain for t. So for example, we just have y equals 2x as a parametric. That's just going to be x of t is t, and y of t is 2t. Done. Alex? Well, that would be saying that every x coordinate is 2. For the line y equals 2x, that's not the, right? The points on that line are like 0, 0, 1, 2, 2, 4, etc. So the t that I'll pick, I can pick any value for t, right? And that'll give me my y or my x coordinate, which should be like, would be the same as the domain for my function, right? Where if the t's and the x's are basically the same thing in this function. Is that okay? Amanda? If your rectangular is a function. If you had like a circle, then it's not as, no. But if it's just a regular function, if it's like a polynomial or a logarithmic or exponential or any of these things, then yes, you can use that shortcut. Going the opposite way is a little bit more difficult. So if we have some parametric function, what you want to do is eliminate t from the system x of t, y of t. So for example, if we had x of t is like 3t plus 2, and y of t is 2x squared minus, or I'm sorry, 2t squared minus 5, I'm going to take the equation for x and write that in terms of t. So I'll just subtract the 2 over and divide by the 3 to get the t by itself. And then I can plug that into the y equation. And then I can simplify and I'm into rectangular form, right? Is that okay? Sophia? Okay. So the only really tricky part about something like this is getting the domain and range for your rectangular function. So let's say that the interval of my parameter was -1 to 5. So the domain is going to come from my x function. So if I look at that x function, what kind of function is that? 3t minus, or 3t plus 2. It's a linear function, right? Everybody agree with that? Now, is that linear function going to be increasing or decreasing? Increasing, because the slope is positive. So I know then the farthest point on the left that is defined is going to be my minimum, and the point on the farthest right would be my maximum if I plotted this as like a t-x axis. Everybody okay with that? So if I just do x of -1 and then x of 5, that tells me that my domain here is -1 to 17. My range is going to come from my y-coordinate. So I'm going to kind of think about it the same way. So I'm going to think about this as like a ty axis. Now, what kind of function is 2t squared minus 5? That's quadratic, right? So does that quadratic open up or open down? Up, because the leading coefficient is positive. Everybody agree? Now, the interval that I'm looking at is from like -1 to +5. Everybody's okay with that idea? So my minimum value and my maximum value is there, right? Everybody agree with that? So to find this vertex, since this is a quadratic, I'm just going to do -b over 2a to give me the x coordinate. Well, the b value here is, in my quadratic, is 0, right? Because there's no x or no regular t term. So my vertex is just going to be at, oops, I don't want to say x there. It's going to be t. Is going to be 0. And my, which is -5. And my maximum here is just going to be y of +5. So that's 25 times 2 minus 5, or 45. So my range then is just going to go from -5 to +45. So again, what I'm doing is I'm taking my parametric function and I'm finding the minimum and maximum values for the x coordinate by using the values that t is defined on, and then the minimum and maximum for the y coordinate using the values that t is defined on. oftentimes it's going to help to draw a little picture of like a tx graph and a ty graph, like I've done there, to help give yourself some intuition, particularly if like symbolically you're not super duper strong, but graphically you're like, if I have a picture, I can figure this out. Sketch a little quick picture, right? It doesn't have to be super duper accurate. Like I didn't plot any points or anything to do this. I just kind of like, what shape is it? What's it going to kind of look like? And then penciled something in there and was done, right? Does that feel okay there? That was like the first 2 sections or something, right? Was doing stuff like that. Okay, and I think that honestly that what we just did was, if not the hardest thing, sorting out those domains and ranges, then the second hardest thing. Keaton. Is it related to this topic? Okay. Can I know you have lots of questions. Can I hold you for another minute?
Yeah.
Okay. So that's parametric stuff still. Let me do. And then we did some converting between polar and rectangular also, right? Oops, that's not the second. Those aren't the notes I'm looking for. I just want to double check exactly how we did. Don't want to get anything confused. Okay. So the key here was these 3 relationships. Say it that way, I should say it. So these 4 relationships were kind of coming back and forth between polar and rectangular coordinates. So Keaton, one of your questions was you had wanted to convert r equals to, what was it? Cosine?
It was r cosine.
Okay, r cosecant equals 2. Okay. So let's do that. As an example. So we're going to try to convert this into a rectangular coordinate. So what I'm going to start by isolating the r. So I'm going to multiply both sides by sine theta, because I know that sine and cosecant are reciprocals. So when I multiply both sides by sine, the cosecant cancels out. Everybody okay with that? Okay. Now I'm going to multiply both sides by r. Oops. I was supposed to write r squared there. So that I can get that r squared. And I can make the substitution to get rid of the r squared and turn it into x's and y's. Are we okay with that? Okay. Similarly, I notice I have an r sine theta, so I can use that to get rid of this r sine theta and replace it with a y. Now I've gotten rid of all of my r's and thetas. The last piece of this is to just get this into the form of a circle. Since I have x squared and y squareds here, subtract the 2y over. And then I'm going to do the completing the square piece. So what I'm going to do is I'm going to add and subtract -2 divided by 2 squared Again, if I'm adding it and then subtracting it, really I'm doing nothing at all, right? Just basically just added a 0 there. And what I'm going to do is I'm going to kick out that piece at the end. It's just -1. So that piece there factors as a perfect square. So the two numbers that multiply to give us 1 and add to give us -1 are -1 and -1 as y minus 1 quantity squared. And as you so astutely pointed out, again, -2 divided by 2 squared is just 1, so I have just a -1 at the end. And then if I just add, oops, that was a plus sign there. I add the 1 over, and I'm done. So I'm sorry, can you say that one more time?
So when you're trying to turn that whole quadratic thing back to like y minus 1
when you're factoring it.
Yeah.
So this piece here is that same number every time.
Oh.
Whatever that thing that you divided by 2 was in squared is the constant when you do the factoring. It'll always be that way because it's always that way for a perfect square factoring. So that's one of the reasons why I left it as -2 over 2, because it'll always transfer down to do the factoring. So if you have a stupid decimal where it's like, shoot, I don't know the two things that multiply to give me 25 over 4 and add to give me 5 over 2. You know, like, who knows that? Doesn't matter. It's 5 over 2 or whatever, you know, whatever. Yes, Alex. So this value is b over 2 squared. So in this case, our b was -2. You have to add it and subtract it. So that, or add it to both sides. You could think about it that way also. That would be fine. The reason I like to do it there is if you had a coefficient here, then adding it to both sides isn't quite right. So I always think about it this way and then think about kicking it out of the parenthesis because I won't be apt to forget about the coefficient. But I don't think that happened on any of these problems, and it certainly wouldn't happen on the test. Well, yeah, so what you really have is this that factors to that, right? Because this is just y minus 1 times y minus 1. So I just shortcutted through some steps because it is a perfect square, so I know how it's going to factor every time. It's not like I have to think about this factoring problem. It's like I know it's going to factor exactly this way because I designed it to factor that way. Yes, sir.
You do r equals 4 sine theta minus 8 cosine theta?
Sure. Yep. Say it one more time. R equals
4 sine theta minus 8.
Okay. So I would start by multiplying both sides by r. So I can get my r squared in there. And then the r squared becomes x squared plus y squared. The r sine theta becomes y, and the r cosine theta becomes x. Good with that? Then I'm going to move it all onto one side, and I'm going to have two separate completing the square problems to deal with. So when I complete the square for the x's, I'm going to be adding and then subtracting 8 over 2 squared. Hi. How are you?
Good, how are you?
Just fine. Elizabeth Housey, you got to get out of jail free card. Oh no, it's a meeting card. Never mind. Sure. I think they want you in just a minute, so. Of course they do, right? And then to complete the square for the y's, again, we're going to do b over 2 squared, added and subtracted. Trev, you still doing okay? All right. We're going to boot that last piece out of both of them. Now this is a perfect square that factors into 8 plus 8 over 2 squared. And then I still have this, which is 16. This piece is going to factor to y minus 4 over 2 squared. And then this piece is 4. Now 8 over 2 is just 4. And 4 over 2 is just 2. And negative 16 and negative 4 is negative 20. And when I add it to the other side, it's positive 20. And there we go. Is that okay? So again, the worst part there is just remembering how to do the completing the square piece. But after you've like figured it out and done it a couple of times, it's really pretty easy. Like you won't have any yucky situations where you're running into like coefficients on top of fractions or something. Occasionally you might encounter a fraction, but not so bad. Does that feel okay? Everybody? Yeah. And then did we do, I can't remember, do we do polar, we did polar to rectangular. Do we go rectangular back to polar? I don't think we do that, do we?
Yeah.
Did we? Oh, we sure did do that. Yep. Yep. But that's not bad. Okay. So if we want to go the other direction, let's go back over here. Oh, sorry. Rectangular to polar. So let's say we have something silly. Oh, you want to just give me one? Sure. Negative 2x plus 3. Cool. Okay. Y is sine theta. X is r cosine theta. So far, so good. Okay, I'm going to move the r's so that they're on the same side. So I'm going to have r sine theta plus 2r cosine theta equals 3. I can then factor an r out. And then just divide both sides by r, or sine theta plus 2 cosine theta. And there we go. So I just divided both sides by this to get the r by itself. Keaton?
I don't know if it's a mistake in the answer key, but the answer key for this problem is in the denominator.
It says it's negative, what's it? Subtracting the 2?
Yeah, it says 2 cosine theta minus theta.
Right, let's go look at the review. What number is this? Oh, on the homework?
Yeah.
Okay. 77. Okay, and then let's look at the problem. See you later. Tell them hi. Oh, it's, yeah. Oops. Yeah, I see what I did. So when I multiply, what did I do? I think it just might be a typo. Yeah. Yeah, I think that's got to be a typo. Look at this real quick.
I feel like one of the longer ones is like 81.
You tell me the numbers.
Yeah. X minus 4 to the second. In parentheses.
X minus 4 to the second.
Plus y plus 1 to the second equals 17.
Did you say minus y plus 1 like this? That's got to be a plus,
yeah,
right?
Plus.
Okay.
Equals 17.
Okay. So I'm just going to start by foiling this stuff out. Remember, x minus 4 is really, x minus 4 squared is x minus 4 times x minus 4. Same thing with the y, or the y plus 1 squared. Is that cool? Okay. So I'm going to subtract the 16 and 1 from both sides. And then I'm going to do a little bit of rearranging. So when I subtract the 16 from both sides and the 1 from both sides, I just get 0 on the right-hand side. You good with that? The x squared plus y squared can become r squared. The x can become r cosine theta, and the y can be r sine theta. And then I'm going to move the 8r cosine theta and 2r sine theta over to the other side. So add the 8r cosine theta and then subtract the 2r sine theta. And then I just divide both sides by r. Remember, why is it okay that I'm doing this? R is a radius, so it's always non-zero. So if I divide by non-zero, that's okay. Normally we don't like to divide by 0, or divide by a variable, right? In your Algebra 3-4 class last year, if you tried like solving a polynomial equation by dividing by x, you missed solutions quite frequently. Here we don't have to worry about that though, because we're not dividing by anything that could be 0. And we're done. Is that okay?
Yeah.
Okay. All right, so that's about how we move back and forth between the two forms to rectangular. We don't need to talk about graphing, right? The graphing the polar things was fine. Okay. If you change your mind, you can always come find me and we can do this some more. The last topic, the last thing that we would have still needed to touch on was the story problem stuff probably, right? So the last section I would say like you can do stuff with, but it's like just following the formulas in there. And the formulas I think are in the equation sheet, so it's not such a big deal. So do you want to do one of these story problems here? Okay. You tell me, guys. I'll do whatever you want me to. Hold on. 82 feet per second. What's the height? Okay. And the angle was 59? 39. Okay. Okay, keep going. I'm sorry, you just said a lot of numbers there real quick that I was trying to jot down.
Oh, that's it. Well, like, you want to find a pair of parametric equations.
Okay. Okay, so let's stop there. So the equations that I'm looking for are the projectile motion equations on page 8 of the lessons. So this just says f of t. I'm sorry. We should use like s of t because this is a position. Maybe. is x of t. Yeah. So this is the form.
Will we be given like the one for this kind of problem?
Whatever the equation sheet that I'm giving you on the test is on the review. So whatever's on there is what you're getting. I don't remember if what I put on there or not, to be honest with you. So here, my initial is 82. My theta is 39. And my initial height was 3. So there's my answer for the first part that it asks for, right? That's like part A or something for this question, Keaton.
Yeah. So the velocity only goes into
The velocity is the 82. It's here and it's here. Yep, cosine theta, which is 39 in this problem. Yep. Yeah, I wrote it that way because I didn't want you to think that it was cosine of theta times t, that it's like cosine of theta and then times t rather than cosine of t theta or something. Right, the order of operations matters there a little bit.
What is the
Yes, that's always the same. Yes, sir. No problem.
B is will the vehicle clear a 15-foot wall that is 205 feet away?
Okay, pause. The wall is 205 feet, and then the height is 15 feet. Okay, so 2 different ways you could do this.
It also wants to know.
Yeah, we can analyze that at the end. So one way we could do this is we can see how long it takes the baseball to go 205 feet. And then we can take that value of t and plug it into y of t to figure out how high it is after that amount of time. So we'll be able to compare that to the 15. And, like if y of t is between 0 and 15, it doesn't clear the fence. If it's greater than 15, it does. The other option is you could take your y of t and set that equal to 15, solve for t, and plug that into the x of t, and see if that number is greater than 205. So basically we're seeing where is that ball at 205 feet. Is that going to be past, is it past or when is that ball 15 feet high? Is it past the fence or not? I usually like to go this direction because it'll allow us to answer the part of that question that Trevor had kind of peeped on a little bit easier, because we'll know the height at 205 feet, so we can tell if the ball is going to be caught or not. Because if that number is less than 205, we don't know how high the ball is at the fence. It could still be 12 feet up there and the guy can't catch it. Versus if we go this route, we'll know exactly how high the ball is.
So getting the x, that portion, so you have to is that all height and the other one?
Right. So in the equation that I boxed, we're going to be assuming that the ball goes 205 feet. figuring out the height at 205 feet. The other option that we had was figuring out how far the ball goes to get to 15 feet off the ground. So it's just, both of them work in answering part B. It's just which one you want to do. Typically, this is the easier route, especially if you're going to be asking about, like, is the ball catchable or whatever at that point. In particular, it's also makes life a little bit easier solving for t in the x equation because it's just a linear equation. Solving the y of t is a quadratic equation, which is a little bit more to do. So t is just going to be like 205 divided by 82 cosine 39. Make sure I'm in degrees. So that's about 3.2 seconds. So then I'm going to do y of 3.22. Plus 3. So when I do that, I get 2.12. So ball's not going to clear the fence. It's only 2 feet off the ground. Shouldn't be a problem for the outfielder to catch that one if he can get back to the fence in time. Are you in degree mode or are you in radian mode? So I did, oops. I had only -6, not -16. Let me input that. So when I do that, I get 988, which is probably still catchable. If you're an adult male outfielder that's pretty athletic, you can probably jump with your arm extended close to 10 feet up in the air if you're like a major league outfielder. That's the height of a basketball rim. If you can touch the rim, you can jump that high. Not unreasonable. Huh? And they have a mitt. Yeah, excellent point. So that's probably still catchable. So Keaton, I typed it all into one line, like exactly the way it's written.
Is there a T after that?
Yes.
Oh, I didn't.
Yeah. See.
Oh, yeah.
Yes, Ava. Of course. So. Like, I haven't finished it, but it'll be like 12 to 14, kind of in that neck of the woods.
So is it more like your review? Is that something, or is it kind of like homework?
Yeah, the homework had a lot of questions on it. The review is probably pretty similar to what you'll have for the test in terms of quantity or in terms of difficulty and type.
Am I putting this in my calculator? I'm sorry, but I got
It's okay.
3.27.
Oh, maybe that's an issue for me. Let me try one thing. Oh, yeah. Yeah, that's strange. What is going on there? So, yeah, I get negative 1,047 or something. Is that what you got, Keaton?
No, I got 3.27.
For the T?
For the T. What?
Oh, cheapers, creepers.
No,
Okay.
For the T, I got 3.22.
Okay.
I think you're right there. But then for the final answer, I got 3.22.
Yeah, I have Let me do that. There. So it should be 343. Sorry. That's what you're supposed to get. Is that what you got, Keaton? Okay, so I used all the decimal points and not just 3.22. So I used like the ands function on my calculator to save all the decimal points. So that's probably the difference. If you were pretty close.
I'm like 3.27. So.
Yeah, that's probably all it is rounding stuff.
Okay, so then we're just going to assume that you can touch it, right?
Yeah, 3.5 feet off the ground, that's like chest height.
And if it was greater than 50, it would be going over the
Be a home run, right. Yep.
Even if it was like 50.
Yep. It hit the top of the wall, that counts as a home run still, right? Baseball players.
What is the back still?
I think even if it hits the top and falls back in play, it's a home run. I think even if it hits like the painted line on the top of the fence, it's a home run.
That's pretty cool. And it's all run, baby.
I don't know. Just like if it hits the foul pole on the home run, I think it counts as a home run, right?
Yeah.
Even if it bounces foul on the foul side of the foul pole. I'm not a baseball expert or much of a baseball fan either, but I think that's how that works.
And then the final part, C, where's the farthest you can place a 10-foot wall so that the ball is clear?
Oh, gosh.
Okay, so what you'll do is you're just going to take y of t equal to 10, solve that value for t, and plug it into x of t. But here, this point, you'll probably get two answers since you're solving a quadratic, and obviously you want the maximum of the two answers, the bigger time. But that's all we're doing. Is that good enough?
Yeah, I can do it.
They're saying, what is the maximum distance you can place a 10-foot fence and still have the ball clear it? So we're going to substitute, we're going to solve y of t equal to 10. So we're going to get an answer for t by solving that quadratic equation.
Oh, we have to plug in y and stuff.
Right. So you'll get two answers. You want the maximum of those two answers. And then you plug that into t for x. And it'll tell you how far away that fence, that wall could be put.
Do you mind doing the algebra for that?
All right. So for my quadratic equation, it's this. Oops. Sorry, that should be -7, really, because I had to subtract the 10 over. So that's like my A, B, and C for my quadratic formula. -7?
Oh, the C equals -7?
Yep. Well, I would do this all in my calculator in one line. And you can even, like, depending on how calculator literate you are, you can do this using, like, storing the values into variables so it doesn't look so terrible. Yeah, you want to see how to do that? Okay. So, like, A is -16, right? So I'm going to type -16. I'm going to press the STO button and store that into the variable A. Yep. And I'm going to do 82 times sine 39. And then press that STO button and store it into the variable B. And then -7, I'm going to do store as the variable C. And then I'm just going to type in the quadratic formula exactly as it states. So I'm going to do -b plus I can't do plus or minus in the calculator at the same time, so I'm just going to do plus and then I'll go back and change it. So we can do that. So there's one value for t. And then I'll just press second and enter. So it'll recall the last thing I typed in. And I can just trace back through here and change that plus to the minus and get my other answer.
Is there any way to graph it and find it off of a graph?
Sure.
Is that like harder?
No, not really. So you could just like type the y equation into y1 and the 10 into equation 2 or into y2 and then find the intersection. Well, this is the answers. 0.09 and 0.84. Yep. You got to make sure the 2a's in parentheses also, and the whole numerator's in parentheses. So again, like I did this with the fraction command where I put in the fraction bar. Like that makes life so much easier. Do you guys know how to get the fraction bar? Okay. Alpha y equals is the shortcut to the fraction menu, and the first option there is that bar. So?
How do you clear like the A, B, and C? What if I wanted to like next column?
You just store it over it. It'll just overwrite it. So if you just do the next one, store whatever the new value is, it'll just replace the old value with the new value. So you don't really need to wipe them.
So this is everything going over to all chapter 10?
Yeah, I think so.
Perfect, thank you. I'll come back to you anytime before the test.
Okay. Do we feel any better about stuff?
Yeah.
I feel a little bit better, but I'm not.
I'm trying, guys.
You're doing a wonderful job.
You know? And then we didn't talk about like the Rose curve or Limassol curve. Those were kind of easy, right? You just needed the formulas. But I just wanted to make sure I point that out, that we didn't do any examples with that stuff. I'm going to leave you guys alone. If you guys still have